Welcome to this talk. Cognition in software operations. Now, when I actually came to write the slides for this talk, I realized I should have given it a cooler name, and that cooler name should have been How to Troubleshoot the Worst Issue of Your Career. So, just a little bit about me first, so that you sort of know where I'm coming from. So, I keep bees, which do have a lot of issues and problems, but that's not where most of my professional experience has been. So I've worked as an SRE at Google and at Slack and some other places that you may not have heard of so much. I've contributed to a bunch of these books about site reliability and software operations. And currently, I'm finishing my master's degree at Lund University up the road. And I'm studying human factors and systems safety, which is a thing that a number of SREs have gotten into, and SREs and DevOps and other software operations folks have been really interested in for the past 10, 15 years. Pretty much ever since Richard Cook and Dave Woods started to get interested in the field. And we had Velocity 2012, if anyone else remembers Richard Cook's how complex systems failed. I think there's been a sort of burgeoning interest in safety science and safety and human factors in the industry since then. So I'm doing this master's degree, and this talk is based largely on what I'm doing for my dissertation. So I'm doing some original research, and essentially what I'm doing is I'm trying to get inside the mind of people as they troubleshoot difficult software problems. So maybe this is a Sev0 incident that has taken down your whole company, or maybe this is just something that's been bubbling away, but you really need to get to the bottom of. If we're in software operations, or indeed in many just software engineers, we spend some of our time doing this work. I think it's really hard work. Some of the worst stuff, or the most difficult times of my career, have been dealing with difficult, hard to understand outages, or even just less severe issues, but ones that need to be resolved. It's very open-ended. You'll always be surprised. And you need to have a lot of different sort of tools to apply to be good at this. So this is one of the worst outages that I've dealt with in my career. This was just after New Year's Day of 2021, the first day that everyone was back at work, and they fired up Slack, and Slack went down. I was the person who called this incident at Slack because I could see that something was happening and it didn't look good. Called the incident, and suddenly everything goes black. Our monitoring is gone, everything is on fire. And it was a very confusing few hours. If anyone wants to know more about this particular outage, which is not the topic of this talk, I wrote a pretty detailed blog post for Slack at the time, and you can go and read that if you like. There's a very short bit.ly link here if anybody wants to check that. Also, I'm going to put the slides are going to be up on the web after this, so you can get all of the slides. So I said that the talk title here should have been about troubleshooting issues rather than incidents per se. So what's the difference? An incident is something like that Slack issue when your site is down or your service is down and it's really broken, huge time pressure. Usually there's a bunch of people who are going to collaborate to get that thing fixed as soon as possible. You're not going to be distracted. Your manager is not going to come to you and say, hey, Laura, it's time to do the quarterly planning. In an incident, this is not going to happen. You're going to be able to fully focus. The other thing about incidents is very often we can do what's called a generic mitigation. We can restart everything. We can roll something back. We can upscale. We can do these kinds of things that very often get us back up and running, maybe a little bit degraded, but they'll get us back up and running. And that is good in an incident situation. But when you're dealing with an issue, usually the time pressure is less. This is something that has maybe been bubbling away, causing subcritical kind of problems. Or maybe it's something where there was an incident and you mitigated it, but you didn't fully understand the mechanism, and now you need to figure out what actually happened there so that you can figure out how to prevent it happening again. So very often something will happen. We don't really understand what's going on at the time. We mash some buttons to make things bigger scale or restart them, but we're kind of like, oh, that's going to happen again if we don't fix it, and we don't really understand it. So we may not have the time pressure that you have in an incident when you're in a room with 10 people or a Slack huddle or whatever, and a bunch of people are like, fix it now. But there's still some pressure. But in this case, the whole point is to understand that causal mechanism, to really get inside what happened and how you can re-engineer your systems in some way to stop it happening again. Normally, you only have one, maybe 2 or 3 people involved in this kind of investigation. This is not the kind of place where you have 10 people sitting in a room, usually. There are exceptions to everything, of course. I also want to make a distinction between troubleshooting and debugging, because we often kind of talk about these like they're the same thing or interchangeable, and they're not, I think. So debugging is if you know that there's a problem, it resides within a specific program, a block of code, and obviously its dependencies and libraries and things. And you can go and you can probably reproduce that on the scale of one program running. And you can attach a debugger, walk through the code, all these things. Troubleshooting usually starts more broadly. It's more usually like, well, this thing is slow. This thing doesn't seem to be doing the right thing. You're not even sure at this point, is it in my program? Is it in the interaction between multiple different services? Is it an interaction with an operating system or something in the network? So troubleshooting tends to cross these system boundaries. And so to be an effective troubleshooter, it's more than just debugging. I mean, debugging is hard too, don't get me wrong, but it's a different thing. With troubleshooting, you have to be willing to sort of follow that problem through different layers of your system. So troubleshooting scenarios, we normally start in one of these places. So something is broken or misbehaving, something is slow, something is intermittently not doing the right thing. This is harder. Something is intermittently slow, also harder. Some subset of what your system is trying to do is broken or slow. So maybe it's requests for customers who are homed on a particular database shard, or customers who have more than X items in their shopping cart, this kind of thing. And you have to sort of sleuth that through. Sometimes your clue is that you have unexplained very high resource usage, or just something else is weird. So I'm going to start off with a troubleshooting story, and this is what motivated me to take this particular direction in my research, to look at individual troubleshooting and how it varies between people, and why some people seem to be more effective than other people. So this story it's a really simple little story in the end, but it does illustrate a bunch of the problems and pitfalls, and also the mechanisms that are involved in troubleshooting. So this is a small organization. I don't work for them. I was involved in this story sort of as an outsider, but I don't work for this company. They had 2 people who had the job title DevOps. They were both fairly junior, and they had a bunch of developers, but they'd had some churn. So this company had been around for a few years, and some of the people who had originally built a bunch of the services had left. So their software is basically all in Java or JavaScript. And they're running on one of the big cloud providers, and it doesn't really matter which. And customers start to notice performance problems, and they start to complain. So this company has one major API service, and it just seems to be sort of browning out regularly. And that's all they know to start off with. So the DevOps team are sort of they're asked by the customer support organization to start looking at this issue. And they go and they look at some of their consoles that they have. And they spot that the APIs, I didn't have monitoring for this, but they are able to see this through their cloud consoles, that their backends in their API seem to be regularly going unhealthy, so they're failing their health checks over a period of several seconds, a couple of minutes, and they're being restarted. And this seems to line up with when the customers are seeing the performance issues, or the brownouts in the service. And they noticed that this had actually started a couple of months previously, and it was ongoing. So this wasn't actually a new issue, it was just newly detected. So this company at the time, they had this sort of pre-existing idea. They were already concerned about their database performance. And so they said, well, the only thing that this service that's going unhealthy depends on is the database. So it must be the slow database. They didn't have a lot of insight into the internals of this service. It wasn't really exporting Prometheus metrics or anything like that. It was just a blob of Java. They did have some logs, but the logs didn't show anything interesting. It just sort of logged stuff. So, is it the database? Database was a red herring. So, they hired a database consultant to look into this and to optimize the queries and indexes and debug all the slow queries that they were seeing, or the slowest queries. And they also upscaled their database instances very significantly. And that didn't help. All their metrics for their database didn't look like it was under much load. It looked really quiet. And there was no evidence of sort of systemic database problems. So that's really strange, right? Then, seeing as they weren't making any progress with the database thing, they said, well, let's look at what happened around the time that this started happening. And it turned out that around that time, they had moved from a virtual machine set up, like where the Java program was running on this big virtual machine, to a containerized setup using a cloud orchestration container platform. So maybe that's the problem, because it lines up in time, and that's a big clue, right? But, so they said, let's revert back and see if that fixes it. But it's really hard to revert back because 3 or 4 months have passed at this stage, and it will be a bunch of work to sort of get things working again on the old platform. So now they're on the horns of a dilemma. They don't really know what's going on. So they're trying to decide, should we invest more in the database thing? Or should we invest all the time to try and get off of our containerized solution and go back onto the VM? Or should we work on adding more observability? Or what should we do? Now, this is the point where I got involved in this story because effectively somebody I know said, wow, we're having this crazy problem at work. And they said, our database is slow and it's making our application completely freeze up. And I said, that does not seem right in my experience. It made me say, no, that's not great. So we got unstuck at that point. And although I didn't know very much about this specific system, I said, if a system is stuck, the best thing to do is to get some thread dumps so you can see what the threads are waiting for, and probably you can go from there and figure it out. And so they went off and they, there was a little bit of friction in actually getting that because their instances were getting restarted when they went unhealthy, but they put in a script to, pull the thread dump whenever the service went unhealthy. And we had a look at it. So the DevOps engineers on this team, they read that thread dump and they were still confused. They thought it showed that the application had run out of threads, like application server threads. And that's how they interpreted it. But I had to look and I said, I can see that these threads, you have many threads, all right, and they are waiting for a database connection. So it turns out that 7 years ago, somebody had added a database connection pool and never configured it. And for 7 years, this service had been perfectly fine running with the default number of connections to the database, and then they had grown. And as they had grown, they had started requiring more database connections, and eventually, at peak time, they were consistently freezing up. And this explained the problem pretty well. We had a look at the database metrics. The number of connections to the database lined up with this theory, and they increased it, and the problem went away. So what can we learn from this? Like I said, it's a really simple case in the end, and the fix was a one-liner. But sometimes somebody who has seen some things can unravel a case really rapidly that has stumped other people for weeks, months, even longer. And I saw a bunch of this in the other cases I looked at as well. Very often a team will get stuck, and an external intervention by somebody who has seen something different in their experience can unstick it. It's very easy to spend a lot of time on red herrings, very easy. In troubleshooting, until you find the solution, which is the whole point, there is always a lot of uncertainty, and uncertainty is difficult to deal with. It requires making decisions, it requires sort of being comfortable with that uncertainty, and it's not very nice, particularly for management, because they feel powerless. They feel like, well, we really need to make progress on this quickly, and we don't know when we're going to have a solution. And very often they'll then start to say things like, well, we must do something, and hiring a database consultant is something. So sometimes management, when they get freaked out about the uncertainty, can make things worse by creating work that isn't pointed in the best direction. So experience can definitely help, I think, to highlight where problems are most likely to be. And in many of the cases that I've been looking at with practitioners, we see that somebody says, well, I don't know where this problem is, but of these 3 things it might be, I think it's most likely to be this one. And they may say this by looking at different kinds of evidence. So in this particular case, I thought it was not likely to be the database when I was told it was the database, mainly because upscaling the database hadn't helped, and because I have experience in my life that, programs can screw themselves up performance-wise very much all on their own without needing resource to any external slow dependencies. So that's different experience that I had had. One of the really important things about troubleshooting is we don't troubleshoot just by passively accepting data, just by looking at the logs and the metrics and things that we already have. Sometimes that does work. Sometimes you get an easy troubleshooting case and it's just, well, this is an error connecting to the foobar service, and you fix the bad config. Sure, that happens, but that's not where people are spending their time. We spend our time on these difficult cases that we can't typically solve passively. So the most effective troubleshooters are comfortable going out and seeking out more data, using things like introspection tools such as thread dumps, profiling, packet captures, and things like that. Then when you have data, you still need to interpret it. And that means that you need to have a mental model of what's happening in your systems. And in software, this is something that people talk about in the research, and I'll talk about this, but in software, most of the time we're all stretched a bit too thin over a bunch of stuff we don't really know thoroughly end to end, and we have a lot of abstraction and a lot of complexity hiding everywhere. So it's normally a case of combining what do we know with what am I finding out. So that's most certainly a thing. And we only know we're right when the problem goes away. We have to make hypotheses, and then we have to test them. And that's the proof when we make a change and we get the expected behavior, then we know that we're on the right track. So the first thing I'm sort of looking at, so the research I'm doing, what I'm doing is I'm interviewing people, practitioners in the industry, and I'm saying, tell me about a difficult issue that you've been troubleshooting, something that you remember quite well and something where you were actively involved. And so now I have this kind of library of, about 20 people's worst troubleshooting cases. And that's given me a bunch of data about where it is that people have difficulties troubleshooting. So there's this idea of intransparency in systems. And what intransparency means is you can't see into it. You can't observe it directly. And this is something that people talk about in the sort of cognition research, the human factors research, the opacity of systems when they don't kind of show us their state. We cannot observe the internals of our system directly. So that causes all kinds of problems. Like in the case that we've just seen, all this, people can't observe directly that there is a database connection pool. We have to observe that using thread dumps, right? We are stuck initially relying on the loggings and metrics and tracing that's there, or seeking out more information using introspection. We can add more. We can add more logging, more metrics, that kind of stuff. That can take time. There can often be, friction doing that. So a lot of the very big hyperscaler organizations, they like to release code in a very slow, controlled manner. So if you're, say, at Google and you want to release, put some new debug metrics into an important service, you could be waiting 2 weeks between that PR going through or change list, as we would call it there, and that actually being fully rolled out into production. So that can be a significant source of friction. Profiling and packet tracing and these kinds of things can be absolute lifesavers, or even sometimes just SSHing into a box and using performance tooling. But sometimes we don't have access for security reasons. Sometimes we might need to open ports. We might need to make code changes again. So, for example, in Golang, if you want to profile it, you have to actually enable that in your code. So sometimes, and I've seen this more times than I would like to admit in my career, sometimes you're trying to debug something and your health checks that you set up in your orchestration service say, oh, that's bad, I will kill it, and now your evidence is gone. And again, understanding what we're seeing may require information that we don't have. Logs in particular they're so interesting. We still rely super heavily on logs. So everyone, probably 6 people have been up on these stages this week saying, observability 2.0, now we are all using tracing, and it is a glorious new world. Yes, maybe. But people still, they reach for logs. When you go to troubleshoot, people are reaching for logs everywhere. There were a couple of exceptions at some of the big hyperscaler companies where there are consistent internal sort of metrics and tracing tools. I've noticed that where people have these tools, they will reach for those tools because knowledge of how to use them is socialized and they're universally there. But in other companies where you don't automatically have RPC tracing turned on everywhere on a handy little page you can just go to, people don't tend to reach for these tools because particularly if you're under pressure, time pressure, you do not reach for new tools. It's uncomfortable. But logs are really accessible. Anybody can read a log. It's just a line of text. And it does fix, in many cases, you can find problems using logs. Like I say, the big incidents and issues are kind of like, there's a fat tail here of, this is easy, I look in logs, I see problem. And then this long tail of, oh my God, I don't know what's going on. So logs are great for the easy stuff, but performance problems, logs are absolutely useless for understanding why is my thing slow, because they do not show that. Logs show things that have completed, by and large. They do not show things that you are waiting for. And logs can be very overwhelming. You can get a huge volume of logs. Very often our logs have a lot of errors and warnings that we don't pay much attention to because they happen all the time, they're just noise. So our logs are not clean sources of data. So there's a lot of potential for chasing red herrings based on logs, and I've seen that a lot. And not everything that we care about might be in the logs. So I don't know if anyone's read this. There was an excellent paper, it's about 4 years old, called Failed Through the Cracks, by some systems academics. They did a great study of failure across distributed systems, and they found that the biggest source of weird, novel problems that they could find was developers doing something and silently discarding the error or not properly handling an error. So, if my code is getting an error and I'm just dropping it and doing nothing with it, it won't show up in your logs, right? You're gonna have a mystery there. So there's a bunch of stuff that just doesn't show up there. So I think one of the biggest takeaways from me from this research I'm doing is that we rely too much on logs and we need better tools. So like I've said, this is something I saw in multiple cases. It doesn't happen in every case, but it happens in a significant minority of cases. Like I say, management sort of panic about the uncertainty and they say, well, it must be the load balancer or it must be the database. And then the technical teams that are working on this, even if in their opinion it is not those things, they may have to go and spend days or or even longer, eliminating every possibility to do with what management thinks it is. So they have to, sort of make a case for it not being that piece of the system, which can be quite hard to do because now I'm trying to prove a negative, right? Like I said, uncertainty. One of the things that effective troubleshooters do is they are able to, and I'll talk a little bit more about this when I talk about the research stuff in a moment, it's greatly increases your effectiveness if you're able to keep your mind open to the possibility of multiple potential causes. If you overfixate on something too early, you can waste a lot of time on red herrings. So it's okay to have a theory, but always look for evidence that your theory might be wrong and be willing to change your mind. We also have to deal with uncertainty about potential effects of things that we might do. So one of the cases I'm looking at, somebody took this, it was a case of a highly sharded data store, and one of the shards had a low persistent error level, and one of their generic things that they do is they restart shards in that state, and it got much worse because the low level of errors was the fact that this thing wasn't accepting writes, and when they restart it, it's no longer doing reads or writes. So you got to think about the sort of effects of actions that you take, and which is also a source of uncertainty. Another theme that crops up is there are parts of our systems that we don't even know exist. And I think every system I've worked on, I've at some point been surprised and gone, we're using that? So in this case, it was the database connection pool. In other cases, it's been other things. I have a wonderful case where a very, very, very experienced troubleshooter who is extremely good at this was derailed for a long time in finding a very gnarly problem because his service had a dependency, and he understood that this dependency was there, but he didn't understand how exactly it worked, and it's crazy. It turned out to be regex on an error message, and somebody changed the error message. But yeah, don't do that. That's my advice. There's always a good reason, though, right? You got to get your work done. Configuration. A lot of issues that are difficult to deal with stem from configuration because configuration can kind of become invisible, particularly certain kinds of configuration. So if you're an application-oriented team and you've got a DevOps team that's working with you, your DevOps team will tend to care about things like the orchestration and maybe like sort of kernel level settings, that kind of stuff, your load balancing. And you as developers will tend to care about your application code. And you probably have some sort of programming language runtime or compile options. Who owns those? In many organizations, the answer is nobody likes those. They are red-headed stepchildren. Apologies to anyone who's red-headed. They're rarely considered. The defaults tend to just work for a long time, and then we get a surprise when they don't. And think application level configuration, like these database connection pools, are another good example of this. So what's interesting is we don't see them very often. We don't tend to have awareness. They don't tend to kind of show up in metrics or graphs that we look at or in logs. They're there and they're influencing things. And based on what you see of how they influence the world, you have to sort of work back and figure things out. One very interesting case I have, an absolutely enormous and expensive project at a big cloud company, failed as a result of misconfigured operating system settings that nobody had noticed for years, and that were causing these persistent performance issues that nobody could troubleshoot. So yeah, configuration is a pain point. This is not just small companies, this is every company. DevOps teams. DevOps teams very often get handed any sort of unexplained issue, particularly if it seems like it's performance or slowness, because they're judged to be the best place to deal with this. So there's sort of an implicit assumption that if you have a DevOps or SRE job title, you are good at troubleshooting, but that's not the case always these days. So to 15 years ago, when I was coming up, everybody was, people who had been working in their university computing club and was used to debugging issues for years and years because that's what they had been doing. Running things on bare metal and, things breaking, right? We have a generation now of people who have these job titles and have come up as sort of cloud infra engineers or mostly worrying about CI/CD systems. And we are losing these kinds of old school troubleshooting skills a bit. So what I've noticed is that a lot of organizations seem to have what I call go-to troubleshooters who are, old graybeards who have seen some stuff and who are kind of comfortable with this kind of work. And there's interesting questions about what happens when these folks retire, I think. So I think one of the biggest underlying issues, and this sort of underlies a lot of the issues with configuration and transparency, is that the observability tools that we have, they tend to show us the state of the world, like a snapshot, or the state over time, like a graph or something like that, or logs. What we are actually trying to do as troubleshooters is we're trying to figure out how did the system get into that state. And sometimes that's straightforward, but a lot of the time it's not. So it requires us to sort of synthesize what we're seeing about the system with what we know in our mental model, and that's hard work. Okay, so there is cognitive science research about troubleshooting. Almost none of it is to do with troubleshooting in software systems or computing systems. The research that does exist in that arena is mostly geared towards the collaboration side of incident management. So if you're going to declare an incident and 10 people will be in the room, how do we best deal with that coordination aspect? But I'm trying to get inside the people's brains. So the relevant keywords are sense-making and decision-making. This is the absolute classic research. This is the model of from the 70s and 80s built by Jens Rasmussen, who studied nuclear reactor operators over in Denmark. So this guy's basically the father of modern kind of safety science and human factors. So his idea is that we have skill-based behaviors, which are sort of rote behaviors, things that we don't even have to think about that we're just able to do. Trivial things like hacking a page when paged, logging into a system, running very well-known commands that you would use frequently. It would also, if you're a pilot, it would involve, say, things like the physical skills of piloting a plane. Then we have rules. So these are things like when we recognize something that we're sort of trained to deal with or something that's routine. So we notice that the situation matches something that we've seen before, and we follow the rules. So in our context, that would be things like we have a run book for this situation of how to upsize the instances, or I have this well-known error coming out of my open source software package. I'll go and I'll read up about it on Stack Overflow, that kind of thing. Knowledge is what we fall back on when we get beyond the rules. So we don't have a skill-based response, we don't have a rule-based response that covers the situation. So now we need to freestyle it. We need to use what we know to start making decisions and to make sense of the world. So we use our knowledge to come up with a plan, and then we might use rules to do sub-goals. We might say, okay, well, based on what I see about this system and what I know, I think that we need to upscale the database, and you probably have some rules on how to do that. So SRK that we've just looked at, it kind of seems to make some sense. But it's actually pretty old, and a lot of people now think that it's not really how we work, funnily enough. Gary Klein is a psychologist who has done a lot of work on how people make decisions and make sense of the world in various fields. So he's done a lot of work with firefighters. He's also done work with intelligence analysts, also housewives or homemakers, all sorts of people, doctors as well. So this is his model of called recognition primed decision making. So here we do pattern matching to match the current situation to something we've seen before, and based on that we queue a bunch of reasonable courses of action that we can take. Then we do mental simulation to decide which one of these processes might be the best thing to do. His point about this really is that this is a very fast process. We don't sit down typically if we're under pressure and say, well, I could do A, B, or C, or D, and I will spend 20 minutes like thinking about the pros and cons of each. Inexperienced people may do that, but an experienced person will just say, okay, we'll do C. That's the best thing to do. And they're doing it kind of almost subconsciously. They don't even think really about A, B, and D because they will recognize that C is the thing that is called for in this situation. So people doing decisions in this way don't often even think that they've made a decision. It's just sort of subconscious. This is one of the things that it becomes very hard for junior people to follow senior people when they're doing this process because they don't have the same context of, they don't have the same sort of library of experiences to draw on. So think about the case in our case study. When I say, well, obviously thread dumps, that's something I have experience with in the past, but the DevOps team in this case had never used or seen a thread dump, and it didn't occur to them that that's a course of action that you might take. So the mental simulation part is an interesting one. We use mental simulation to evaluate whether a potential course of action might work, and if the answer is no, we'll go back and we'll think again. And we also think about, will it have bad side effects? Can we modify our course of action? There are limits on how much mental simulation we're able to do as people. You are able in your brain to think about roughly 3 system elements or moving parts and maybe 6 steps in a process. And your brain is not really big enough in its working memory to deal with more than that. Like, these are very real sort of hardware limitations almost. But very experienced people are able to cheat the system, and because they have seen more system behavior and they have this bigger library of experiences to draw on, they're able to think about their mental simulations and their processes in bigger chunks. So where a novice might say, upscale the database, that's 6 different steps, and that's all they'll be able to think about. Maybe I've done that 20 times before, and I say, okay, I upscale the database, and that takes up 1 slot in my brain. So you're able to sort of have this hierarchy. Experts also process information really differently. We are able to see what are called super signals by Dietrich Dorner, which basically means that we're able to chunk together a bunch of incoming data and interpret it as one signal. So I might say, look at 6 load balancing metrics from a proxy and say, okay, well, I can see from that this backend here is probably slow, even if there isn't a latency metric on there. So that's something that we've seen before. Super signals can also be about the absence of events or things like volume. So I've had people say to me, well, as soon as I saw that the log volume increased, I knew that it was a problem over here. So the most recent thinking is this data frame theory. So this is about sense-making rather than decision-making. So sense-making is how we make up stories that explain what's going on in our systems or in the world. So it's about elaborating and adding more detail, about questioning when we think our current account may be wrong. And we also use this to sort of compare alternative accounts of events. So is it the database or is it something else? So a data frame is it could be a story, a map, or a plan. It's a way of relating things. They relate your load balancer to your database to this problem that you're having, and they guide the search for more information. So the frame that you're in tells you what information to go and seek out. So we tend to anchor them on a small set of important data. So we had several frames in the case study that we looked at. The initial frame that people came into with was, well, we have performance problems with our database, and now we're having performance problems with this service. Probably they're related. So it's probably the database. And so they anchor on that, and they start looking at their slow queries, and they find some, and so on and so forth. Frame theory can also explain other parts. So the database theory kind of got slightly invalidated when they upscaled their database and it didn't help. So that was something that didn't fit the database theory frame. So instead, they move on to this new frame, which is maybe it's the rollout, and they work from there. Experts have got a better set of frames because they have seen more scenarios. They're able to think about potential kind of causes and potential explanations that novices can't think of because they don't know enough about the systems at hand to have these frames. And sometimes we need to juggle multiple frames and sort of do a differential diagnosis and decide which one is the best. So the way that we use frames tends to also rely on abductive reasoning. So we say, well, we have this collection of facts, we have this explanation, does it all fit together? What is the hypothesis? What would explain what we see? And we're looking for things to be coherent. We're looking for things to sort of make sense as a story. I'm going to skip through some of this because I'm late. So the implications of frame theory are there is no generic sense-making skill. You're able to make sense of situations in systems that you know well enough. It's situated in a domain of expertise, such as software, such as a particular database. A really important part of frame theory is being able to notice the anomalies that say, well, maybe this frame is not the right one. Maybe we need to update this frame. Being able to have a really rich set of frames is probably one of the most important things for being good at troubleshooting. Having comprehensive mental models of your system, it's nice, but it's probably not as important because you can do a lot with a partial model and adding to that the ability to introspect the system and update that model, because that's something we almost always have to do. So, how to troubleshoot the worst issue of your career? Realize you might need to build some new mental models. You might need to look beyond the logs and metrics, and you might be dealing with parts of the system that you don't know exist. With time and persistence, all issues are troubleshootable. Maybe you can ask for help, or if failing that, read docs and reach for some different tools to introspect your systems. When you are done, you will have a richer set of frames. So this is your reward. Over time, it does get easier. So as I said, I have put the slides for this online already, so bit.ly tshoot-worst. And if you want to read more about any of the theory that I've been talking about here, I've given the references and my own contact information if anybody would like to ask any questions later on. Thank you very much for your attention.